Okay, great. So, yeah, thank you for the introduction. And hi, everyone. My name is Ruyi, and I'm super excited here because I will have 2 slots to introducing our recent work on synthesizing efficient algorithms. Yeah, so we will have a lot of time on this topic. Yeah, and at the very beginning of these 2 presentations, I would like to introduce our whole group at Peking University working on this problem. Our final goal is to automatically synthesize efficient programs that may require complex optimizations, such as algorithm level optimizations. Yeah, and we have several people working on it, and we have also received many help from our excellent collaborators, such as Nadia. Should be. Oh. Okay, so and we have made progress from different aspects. For example, we have constructed a dataset including many interesting and also challenging problems. We have designed many synthesizers for different kinds of complex algorithms. And also, we are working on a verifier to automatically verify our synthesis result. So although in these 2 presentations, I can only introduce the progress on synthesis part. But if you are interested in any point on these slides, yeah, let us just discuss later at any time. OK, so let's move to the main part. So in my first presentation, I will show you how to efficiently synthesize divide and conquer algorithm. So let me begin with a question. So please raise your hand if you already know divide and conquer before stepping into this room. OK, great, excellent. So we have many experts on algorithms, so it will make my presentation much easier. Yes, thank you so much. OK, so basically, divide and conquer is a very classical algorithm to evaluate some function on a list. It suggests that we can first divide the input list into 2 halves, then recursively apply the same function to the half lists, and then somehow using some magic combinator to combine the sub-results together. The key advantage here is that the 2 recursive calls can be distributed to different processors. That means that any divide and conquer algorithms, in theory, can be run efficiently in parallel. OK, so this is the overall procedure of divide and conquer. Pretty simple. But the problem here is that writing a divide and conquer algorithm is not that easy. The problem is this combinator can be pretty complex, even for very simple problems. So it can still be a significant challenge for the programmer to write this. To see this point, let us consider a very concrete problem that is second minimum, which our goal is to calculate the second smallest value from an integer list. So solving this problem is nothing difficult, right? We can just write this program by sorting the list from small to large and then taking out the second value in the sorted list. So I believe that every programmer is willing and is able to write such a program. OK, so now the problem is that let's consider what will happen if we want to write a divide and conquer algorithm. That is, how can we get this combinator? Intuitively, this combinator should take the recursive results as input, right? The second minimum of the half lists, and it should produce the corresponding output on the whole list. Yeah, so this is clearly an input output specification for the combinator, and one may use it for synthesis or for reasoning. But the problem here is that such a simple combinator usually does not exist. For example, in this case, we know that the second minimum of the half lists are in fact not enough to determine the whole second minimum. For example, suppose the left list is 1, 3, and the right list is 2, 4. Then the combinator can only know 3 and 4 in its input. But it is expected to produce that value that is unknown for him, that is the value of 2. So clearly, the information here is not enough for such kind of combination. OK, so what we can do if we want to manually apply divide and conquer? So we need to supply more information to the combinator. So one solution is that we can introduce some auxiliary value. For example, we let the divide and conquer algorithm not only calculate the second minimum, but also calculate the first minimum. Right? So in this way, we have much more information. And then, as we can see, the missing value 2 now appears in the input. OK, so this is how we will manually apply this divide and conquer algorithm. And the problem here is that now with the help of auxiliary values, there are many, many more inputs to the combinator, so that it will just make our combinator even more complicated. So the content of this combinator is not important, but we can just compare it with our initial program of second minimum. So clearly, the combinator is much longer and involve much more low-level computations like branches and comparisons. So it would be definitely great if we can automate this procedure. That is, automatically synthesize this combinator just from a user-provided arbitrary reference program. OK, so this is our motivation. And later in the remainder of these slides, I will first show you the formal definition of our synthesis problem, then the basic idea of our approach, Then I will show you some interesting extension of our approach beyond the divide and conquer. And at last, I will show a very brief evaluation. Okay, so the synthesis problem. So of course, our synthesis problem is about synthesizing divide and conquer algorithms, right? So our input is a reference program provided by the user denoting the program they want to write into divide and conquer. And the most important synthesis target is the combinator that can merge the sub-results during divide and conquer into the whole result. But as shown in our previous example, sometimes we still need some auxiliary values, so we need to introduce another synthesis target, aux, to help us specify those needed auxiliary values. And in the specification, what we want to do is to ensure that this combinator can correctly merge the results. That means that for any possible left list, any possible right list, then given the left result, the right results, the combinator should be able to correctly produce the whole results. So if we unfold these results, the left thing should be the reference output on the left list, auxiliary value on the left list, and the right thing should be these two values on the right list, and the whole results should be these two values on the concatenated list. Okay, so this is clearly a synthesis problem. And you know this problem must be difficult, or otherwise solving it won't be a presentation here. So in more detail, the challenge comes from two aspects. So first, as shown in our previous example, this combinator can be pretty complex even for simple problems. And in our dataset, it can be even more than 100 AST nodes, which is pretty large for program synthesis. And on the other hand, this specifications form is not so simple. It includes two unknown programs, and it is in fact relational. So as far as we know, there's no existing synthesizers that can support such a large-scale relational synthesis problem. Okay, so how can we solve this challenge? Our key idea is try to decompose, which is pretty close to the previous presentation here. So our key idea is that somehow maybe you can use some rules to decompose those whole synthesis problem into a series of subtasks, each with simpler form. On the one hand, we can reduce the synthesis scale because in each subtask, we only need to consider a subprogram of some synthesis target. And on the other hand, the specification becomes simpler because in each subtask, there's only one unknown program involved. So this is just a high-level idea, and I will then show you how we can do this decomposition. So following this line, we propose our approach, AutoLifter, that incorporates a bunch of specialized decomposition rules for such kind of specification. And now I will just show you the most interesting one, but there are several else in our paper. Okay, so this decomposition rule, we name it as variable elimination because it can eliminate one variable from the specification. So it is based on two observations. First, as we can see, our original specification itself is already in an input-output form for the combinator. And these input-output expressions can both be regarded as functions related to only to the auxiliary function, the left side list, and the right side list. So they can be just regarded as input and output generators for this combinator. And let's see what we can do with these two generators. So we can just consider several concrete lists, left list and the right list, and then put them into these generators. And then they will provide some symbolic input-output pairs for the combinator, right? And these inputs and outputs will only be related to the auxiliary function. And because there are many, many different input lists in the world, so we can just get such kind of input-output pairs, and as many as we want. So, and following is our second observation, is that whatever this combinator is, it is always behaves like a function, right? So it can only map the same input to the same output. So let us try to write this requirement down. It means that for any two pairs of left list and right list, whenever the output of the input generator is the same, then the result of the output generator should also be the same. So clearly, this is a specification for the auxiliary function, and here we can see the combinator disappears. So we can use this spec to do decomposition. What we need to do is to first synthesize the auxiliary function from its own specification, and then put the result inside the whole one, and then we will get a separate specification again for the corresponding combinator, and then we synthesize it. So a more interesting thing is that both these subtasks are much easier than the original one. First, for the first subproblem, we can just synthesize it by bottom-up enumeration in most cases because this auxiliary function is pretty small. the key reason is that we do not need to be efficient. We only need to be correct to specify those auxiliary functions we need, auxiliary values we need. And for the second subproblem, so it is a very standard program by example task, right? So it is in an input-output form, and both the input and output are known. So we can just extract out many concrete input-output examples and let existing program by example solvers help us solve everything. Okay, so this is the overall idea of the decomposition. And you may have already found that this procedure, in fact, does not use maybe not many specific properties of divide and conquer, right? We do not need to use the property that here is at least concatenation, and there are two lists, and so on. So what does it mean? It means that we can generalize our approach to many other different similar problems. So we find that even though our approach is just designed for divide and conquer, it can in fact be generalized to many other different paradigms, for example, the streaming algorithm mentioned before, and also many specialized paradigms for some specialized problems like the longest segment problems and the specialized data structure, namely segment trees. All of these paradigms, their application problem can be reduced to a core synthesis problem with a similar form where our approach and our decomposition rules can still be applied. For example, let us consider the case of streaming algorithm. So its key idea is to treat the input as a stream and then calculate the value we want just from using a scan from left to right. And in each step, what we need to do is to locally compute the new result using the previous result and the new element we visit. So, and of course, similar to the divide and conquer case, sometimes we need to introduce some auxiliary values to enable such kind of combination. Okay, so we can write this specification down. So the specification here is that for any previous list access and for any new integer, given the previous input of the combinator, then the output should be the new reference output and the new auxiliary values. So, and here is the specification of the divide and conquer. As we can see, they're almost the same, right? Both of them are in the input-output forms for the combinator, and they are both related to two different functions, the combinator and the auxiliary function. So that means that our, at least the variable elimination you have seen can be applied here, and in fact, our whole approach can be applied. So in our paper, we formalize this whole problem as an abstract synthesis problem, namely lifting problems, and we demonstrate that our whole approach can be applied to this more generalized problem. Okay, so let's end with a very quick evaluation. So in our evaluation, we consider all these paradigms we mentioned before, and we collect a data set from previous related studies and also a website, namely codeforces.com. It is an online platform for competitive programming, which is a context for writing complex programs and efficient programs. And our data set including some classical problems like maximum segment sum and some like bracket matching. And also we include some real problems in real competitive programming. And our results just show that AutoLifter is effective in solving these problems. It can solve most tasks using within a small time frame, and this performance is better than previous related approaches. Okay, so this is everything about these slides. So what we want to do is to automatically rewrite a reference program into a divide and conquer algorithm. And also we notice that our approach can be generalized to other similar algorithms. And targeting at this problem, we propose our approach, AutoLifter, which key idea is to perform decomposition to simplify the synthesis problem, to reduce the synthesis scale and simplify the sophistication. And that's all. So thank you for listening, and I'm excited for the questions.
Hi, I just had a quick question about when you synthesize the auxiliary program, is there any backtracking involved? Like, is the auxiliary function that you synthesize guaranteed to be the right one?
Yeah. That's a very great question. So actually, in theory, this procedure needs backtracking because this specification for aux is not precise, right? Because in most cases, we want an efficient combinator, not an arbitrary function. And we do not have any such kind of ensure in the derivation of this separate specification. But an important theoretical result in our paper is that we find that this kind of decomposition is extremely effective in a special case that is divide and conquer producing scalar values. So in that case, we do not need any backtracking. We can solve almost all the problems we have ever known, and we also prove some theorems to justify this observation. Yeah, so in theory, maybe we need backtracking, but in our current implementation, we do not have any of them.
It was a wonderful talk. Thank you. It seems like your approach for the divide and conquer makes like a lot of sense, and I can see how that would solve divide and conquer. And guess I'm curious why you only got not only, but you got the 82 out of 96 examples from your benchmark. Like, what is causing those last ones to fail, given how well matched this algorithm seems to that problem?
Great question. So the problem is that, because in fact our approach just decompose, it does not solving the whole problem from the scratch. It just decomposes the problem into some similar form and then pass it into existing synthesizers, right? We use enumeration synthesizer to synthesize the args and use existing program by example solver to synthesize the combinator. And here, one problem is that it is just a challenge mentioned by Ziten. It is in some cases, the combinator will involve some complex non-linear operations, which can be pretty challenging for existing program by example solvers. And that's, I think, accounting a major part for the tasks we fail.
I see. So very quick follow-up. Like, if you manually looked at those decomposed problems yourself and you were the program synthesizer, could you slot yourself into the algorithm and solve it? Or is there some fundamental limitation where no synthesizer could solve it?
Sorry, you mean the complex combinator or which one?
Yeah, we can take it offline maybe.
Okay, great.
Yeah. Thanks.
Thanks. Very, very nice talk. I have a question about how do you deal with these recursions? Is your combinator a recursive program? And by the way, I have another question. Is that I think your as this auxiliary values very similar. I would say in the field of inductive environment or loop environment, some program cannot prove by a simple specification. You need to strengthen it.
Yes.
Is there some connection of it?
Yes, I feel they have some connections. So in fact, our auxiliary function can be regarded as an environment for the divide and conquer, right? It specifies in each single step of divide and conquer what the input is and what the output is. So it can be regarded as an environment. And for the recursive combinator, so currently we only consider scalar expressions for the combinator, so there is not any recursions. Yeah, and we have also noticed that the auxiliary function we synthesize can be maybe useful for the verification part, which is our another work. Okay.
Since we have a minute, I'll throw in a question too. I was wondering if you had done anything like taking your freshly synthesized divide and conquer programs and executing them. Now you can parallelize them. And if you do that, do you now get faster code than the original algorithm?
Yeah, sure. So on the one hand, in our dataset, the input program, because our approach does not need the reference program to be, for example, linear time or to be efficient. So in some problems, the reference program just run in quadratic or triple times. And in that case, our synthesis algorithm is ensured even run in sequential, it is still linear time. So in that case, it is much faster.
But I mean, did you measure? I mean, in how many out of 81 or whatever cases?
But I mean, in theory, we can ensure that we can achieve linear speed ups in many. Yeah, but it depends on different libraries of parallelization and depends on the device. Yes.
Okay, let's thank our speaker. Okay, our next speaker is Ruyi again. This talk is Superfusion, eliminating intermediate data structures via inductive synthesis.
Oh, wait. Okay, great. Well, so hi everyone. My name is Ruyi, and nice to see you here once again. And let us just continue our topic on synthesizing efficient programs. And I'm pretty excited because I'm going to show our most recent approach and also more interesting approach in this topic. So different from the previous work, which starts from a small point that is a very specific algorithm, namely divide and conquer. In this paper, we tackle a more general behavior of optimization, that is eliminating media data structures, and get a different approach. But at the end of this slide, I will show you that, in fact, our new approach can capture all the problems we mentioned in the previous slide using some interesting construction. Okay, so let's just begin. So to begin with, let us choose a pretty different story to separate from the previous slide. So to begin with, let us just consider two important properties that we want to have when writing programs. They are simplicity and efficiency. On the one hand, we want our code to be simple because we want a low cost of coding and maintaining. And on the other hand, we of course want our code to be as efficient as possible because it means a high practical performance. But what is the problem? Problem here is that these two properties are conflict with each other. To see this point, let us consider a very concrete task, namely maximum tail segment sum. The input of this task is an integer list with some possibly negative integers, and our goal is to select a proper tail segment and maximize the sum of all values in this tail segment. For example, here, the best choice is to select the last three integers, and the corresponding sum is equal to 4. So, yeah, just similar as the previous slide, solving this problem is nothing difficult. So we can just write this simple program following the natural language description of this task. What this program do is to first generate the whole list of all possible tail segments and then convert it into a single, a one-dimension list including all possible tail segment sums, and then take out the maximum. Okay, so this program clearly simple. So it is short, easy to write, and easy to understand. But its problem is that this program is not very efficient, right? It takes a quadratic time, which is not very good when the input list can be pretty long. So if we go to analyze this program, we can find that this efficiency is in fact caused by the huge intermediate data structure constructed by this tails function. This data structure, its size is already quadratic, making the subsequent calculation at least quadratic, because we should at least scan over this whole intermediate data structure. So given this analysis, it means that if we want to get a more efficient program, we should at least compress this intermediate data structure into some smaller version. For example, a constant number of scalar values. And in this way, we can avoid the bottleneck of the simple program, right? Because we can greatly reduce the cost of scan over this intermediate output. So following this line, we may get an efficient program for this problem. And in this program, we totally rewrite this tails function to just return two integers. The first integer is the value of the MTS, and the second is an auxiliary value equal to the sum of all values in the input list. So when running this new tails function, it will first go inside and go recursions, and in the basic case, when the input list is empty, it will just return two zeros according to its definition. And then it will go back and update this result step by step. In each step, it will first calculate the new sum and use the new sum to update the value of MTS. For example, here, the new sum is equal to 2, which is greater than the previous MTS, so the new MTS will be the new sum. And also, if the new sum is smaller than the value of MTS, won't change. So, and in this way, we can correctly compute these two values during only a single recursion, and then the subsequent problem becomes much easier. Because we only have two integers returned, what we need to do is to just use a very cheap projection operator and using constant time to take out the value we want. Okay, so this is what we can do to optimize this optimize the simple program. And as we can see, the new program is much more efficient, which is good. But it also has its own problem, right? It is no longer simple. It is much longer and needs some human intelligence to design a proper tails function. So here is the conflict. So as we can see, in most cases, we can easily write a simple program, but it's always or maybe in most cases inefficient because of intermediate data structures. And also, if we are willing to pay some efforts, we will be able to optimize it into an efficient program, but such a program is usually non-trivial and never simple. In this paper, we want to do something with this conflict. So what we want to do is to use program synthesis techniques to reconcile these conflict properties. In detail, we want to just come up with an optimizer that can automatically eliminate intermediate data structures, then transform from the simple program to the efficient program. And in this way, the user can feel free to write the simple programs, and there will still be an efficient program for the runtime performance. Okay, so following this goal, we propose our approach SuFu, which uses inductive program synthesis as the backend to eliminate intermediate data structures. And this very good name, SuFu, comes from the abbreviation of two related lines of research. They are superoptimization, which uses inductive synthesis to optimize programs, and fusion, which first studies the general idea of eliminating intermediate data structures. Okay, so in the remainder of this slide, I will first show you an overall workflow of SuFu, And then I will show you two very interesting applications of our approach, and finally end with some very brief evaluation. Okay, so the input of SuFu is a reference program which we suppose to include some intermediate data structures. And SuFu also needs a type-level annotation to specify those intermediate data structures to be eliminated. We call it packed data structures. And then given this information, SuFu will first go a round of type-level analysis and then extract out all those expressions that are related to the packed data structure. For example, here, there are three such kind of expressions. There are two constructions happens in the function of tails, and also one consume, which consumes the constructed packed data structure into the final value of MTS. Okay, so after get this analysis result, so we know that our final goal is to eliminate this intermediate data structure in the final program. So it means that all these three expressions should no longer exist in the resulting program, right? So SuFu will just treat it as a sketch and then synthesize to rewrite all these extracted expressions with scalar expressions. And in this way, there will be no longer packed data structure exists in the resulting program, and in our case, we will get the efficient version of the maximum tail segment sum problem. Okay, so this is the high-level procedure, and the key problem here is that how can we solve this sketch problem, right? Because, I mean, the optimizer program is usually complicated, so we face a significant scalability challenge. In our dataset, these new expressions can be even larger than the previous paper, which is a very monster size for a general purpose sketch solving. Okay, so how can we solve this problem? Let us consider an ideal world that we can get separate input-output examples for each sketch hole. Then at this time, we can find that we no longer need to consider the auto sketches, and then we can use program by example solvers to synthesize these expressions one by one and separately individually. So now the scalability challenge is solved, right? Because we have many effective program by solvers can synthesize very large scale scalar expressions. So this is also the secret sauce of SuFu. So SuFu will use a series approach to extract out separate input-output examples for these sketch holes and then pass them to existing solvers. To achieve this, SuFu will first synthesize a helper function, namely we call it a compression function, and then use this compression function to generate examples. And intuitively, this compression function just specifies how we will compress this packed data structure into the final program, into the final version. For example, we know that in the reference program, the packed data structure is the list of all possible tail segment sums, all possible tails. And what we need to do is to compress it into two integers, the value of MTS and the value of sum of all, and the sum of all possible values. So the expected compression function here should take the left side list as the input and then correctly produce the corresponding two integers on the right. So later I will first show you how this compression function help generate input-output examples, and then I will go back to the problem of synthesizing this compression function. So for simplicity, let us just consider the third sketch hole and recall that our final goal is to rewrite this sketch hole with some scalar expression while keeping the global input-output behavior of the whole program unchanged. So what we can do here? We can first generate a bunch of random inputs and run the sketch program, and meanwhile we keep the track of the whole execution procedure and record all input-output pairs of the original expression here. For example, in this case, we will know the original expression maximum epsilon TS will produce value 1 when given this nested list for TS. Okay, so because we want the global input-output behavior unchanged, so an intuitive idea is that maybe we can just use these input-output pairs as the input-output examples of the new expression. But here is a gap. So because in the collected input-output pairs, there may be some packed data structures which no longer exist in the resulting program. But our compression function can help us bridge this gap. So because the compression function just declares how we will compress each packed data structure. So what we need to do is to just apply the compression function to each involved packed data structure, and then we will get a very concrete input-output examples for this separate sketch hole. And then the later problem is for the program by example solver. Okay, so this is the overall example generation procedure. And it looks pretty effective. And the only problem remaining is that how can we know this proper compression function before synthesizing these sketch holes? Okay, so recall that the only role of this compression function is to generate input-output examples for the new expression or the new sketch whole. So of course, we want the later synthesis procedure to succeed, right? Or otherwise, the overall optimization procedure will fail. So it means that this compression function should at least ensure a realizable program by example task for the new sketch whole. That means that there should at least exist some program that's satisfying all input-output examples collected. So to synthesize from this specification, as we can see, our previous idea of variable elimination in the previous presentation will help. So here, this specification is in an input-output form, and also we can see that this new expression, whatever it is, its input-output behavior must be a function. So again, we know that this function must map identical inputs to identical outputs. So by writing it down, we get a specification of the compression function, and we can just synthesize it by bottom-up enumeration. So this is the overall workflow of SuFu, and so it first uses this specification to synthesize a proper compression function, and then feed it to extract out input-output examples, and then separately synthesize each sketch whole by program by example solvers. Okay, and then so there are also many details remaining, but let us just pause that here, because I want to use the next several minutes to show you two very interesting applications of SuFu. So the first application is just our topic in the previous slides. That is how to automatically apply some algorithmic paradigms to rewrite some reference program. So with the help of the SuFu as the backend, we can write a magic function called apply, divide, and conquer, which can help, which intuitively can apply as apply, divide, and conquer algorithms. Whenever the user want to rewrite some part of their code to be divide and conquer, they only need to apply this magic function to the function they already implemented. And then SuFu will help them generate the very specialized and very efficient divide and conquer algorithm. And the magic thing here is that the user does not need to know anything specific about SuFu and divide and conquer. And in this interface, there is even no packed annotation exist. So what is the secret here? So it is, in fact, pretty simple. So the core of this function is a template of divide and conquer, which only calculates the identity function. So as we can see, every time when we split a list, it will just concatenate back the recursive results. So that means that this function will always map any input list to the identical input, to the identical list. And then given the reference program, this function will just compose this reference program with the template function, and then mark this intermediate data structure here as packed. So let us consider what will happen if we apply SuFu to eliminate this intermediate data structure. So at first, during the elimination procedure, this function divide and conquer can no longer produce this whole list, right? Because they will be compressed. So it will force it to directly calculate the final output of the reference function, and then resulting in a very specialized divide and conquer algorithm for this reference function. So with a similar construction, we find that any paradigms we considered in our previous work can correspond to some apply functions constructed in this way. So that means that SuFu can solve all of these problems. So so in other words, SuFu is strictly more generalized than our previous work, AutoLifter. And another very quick application is that SuFu can also be applied to synthesize some interesting native interpreter for simple DSLs. So suppose that we have a host language where we know everything. For example, we already know the interpreter of this function, of this language. And one day we constructed some DSL over this host language using some syntax sugar, and which means that we will know a desugar function from the DSL to the host language. And what we can do here is to compose this desugar function and the interpreter, and then mark the intermediate program in the host language as packed. And then SuFu will just help us eliminate it and generate a native interpreter just from the DSL directly to the values. Okay, so let us end with a quick evaluation. So in our evaluation, we consider three sources of benchmarks from previous work of Fusion, and also two datasets in the context of program synthesis, where recursion is from a dataset of synthesizing recursions, and the divide and conquer is just our previous dataset for synthesizing divide and conquer and similar algorithms. And our evaluation results shows that SuFu is pretty good at solving these problems. It can solve almost all, most tasks. And also compared with sketch solvers, SuFu is much more effective And also even compared with specialized approach for some of these sorts, SuFu can even solve a competitive number of benchmarks or even a more number of benchmarks. Okay, so let's end with a summary. So this work is motivated by the conflict between simplicity and efficiency, and we want to use program synthesis to help us eliminate intermediate data structures, and in this way reconcile this conflict. And our approach, SuFu, takes a reference program as input and also some type-level annotations, and it can help us automatically generate an efficient version without these data structures. And we have seen two interesting applications of SuFu, which can be used to apply paradigms and also can be used to synthesize some simple interpreters. And now you can try SuFu very easily just through this IP address or scan this QR code. Yeah, so if the server down now, I will try to fix it within 10 minutes. Okay, hopefully it is not the case. And so thank you very much. My name is Ruyi, and I'm so glad that I can give these two talks here. And I'm very excited for the questions. Thank you.
I have one question to the three previous talks. So that's very efficient, isn't it? So 2/3 of them to you. So some of the synthesis problems are reminiscent. You basically have an incremental problem, which is like you have a function and somebody changes the input.
Yes, exactly.
And there's a lot of techniques that have been explored, and
exactly.
that go back to the 20th, 19th, and actually 17th century.
Yeah, from
so
the community of fusion, right?
Pardon?
Fusion and the incremental computation.
Yeah, incrementalization and finite difference from a differentiation. They're used. Have you, have you compared what can be solved by these, algorithmic techniques? Because many of the examples that I saw, at least here, would be amenable to that.
Yeah. So we have explored some of the previous approach, and one motivation for us to use inductive synthesis is because we find that previous approach mainly use some, for example, program level transformations or some syntax level predefined transformations. And they are not so good as those complex problems that may require imposing some auxiliary values, because these auxiliary values depend on specific problems and they can hardly be captured by predefined rules. So in this paper, we just consider to reformalize this whole problem as an inductive program synthesis problem and then solve it efficiently using our approach. And also we have some evaluation results in our paper that show that our approach can solve more problems than previous fusion approach, which based on syntax level transformations. Yeah.
Have you compared against the kids and the wrapped systems from the 1980s? Probably not, because they don't exist anymore.
Yeah,
okay.
We compared with a pretty recent fusion system that is about.
Wrapped is automatic. Well, it doesn't exist.
Yeah. But we can try to explore this approach later after. Yeah. Thank you.
Just a quick question. I was wondering, how did you get the signature for the new one? It was like an int tuple of ints. I didn't see how you got that. Was that something that the developer annotates, the pair of ints?
You mean the signature in the final program, right?
Yeah. Is that something that the developer puts?
Yes, this is exactly the output type of the compression function.
But the developer writes int.
No. This is just rewritten by SuFu.
Okay.
So the whole write program is generated by SuFu, and SuFu will also rewrite this packed necessary list into int times int. So it is not.
So you also search over the set of possible output types?
Because
how do you know that?
Yeah. This is because during the synthesis of the compression function, we will have a bottom-up enumeration to synthesize it, right? And this bottom-up enumeration does not limit the output type into a very specific type. It can be any scalar type. For example, it can be int, can be boolean, can be pairs of int. And then once we find a proper compression function satisfying our specification, then this output type will be the resulting type of this packed data structure.
Okay, I see.
So let's do one more, but please try to make it quick.
Yeah. Thank you for the amazing talk. I just have a quick evaluation question. So I know Farzen et al. Has a few papers on divide and
Synthesizing
conquer
divide and conquer.
synthesis, right? So
Yeah,
I
yeah,
wonder
right.
if that is in
Actually,
your benchmark set.
we compare it with Outlifter, our previous approach.
Oh, I see.
Yeah,
That's right.
and we just find that, of course, first our approach requires less inputs than that approach, right? That approach requires single pass programs, and single pass programs itself will involve some auxiliary values. And on the other hand, the number of tasks we solved is competitive with their approach. Yeah, you can find the detailed result in the Outlifter paper.
Great. Let's thank our speaker again.